All right, this is the Taylor series practice worksheet. The first problem says find the fourth Maclaurin polynomial for natural log of 3 plus 2x. So n is 4. Maclaurin means the center is 0. And we have a natural log function, so we need to find, we're going to be building this thing, right? So we need to find, first f of x is ln of 3 plus 2x. So we evaluate at the center, which is 0. So that gives us ln 3. F prime of x is going to be, so it's going to be 1 over 3 plus 2x, but then you multiply by the derivative of 3 plus 2x, which is 2. And then f prime of 0 in that case would be 2 over 3. We have to do this for 4 derivatives. So second derivative. So now this is like 2 times 3 plus 2x to the negative 1. So it's going to become negative 2 over 3 plus 2x to the negative 2. So putting a square down there. And I have to multiply by 2 again because of chain rule. So f double prime of x at 0 is going to be negative 4 over 3 squared. Now I want the third derivative. So this negative 2 is going to get multiplied by this negative 4 to give us positive 8 over 3 plus 2x to the third. And again, we're going to multiply by another 2. So that's going to give us 16 up there. So the third derivative at 0 is going to be 16 over 3 to the third, which is 27. And I can just get the fourth derivative in here. So this 16 will get multiplied by negative 3. This will become 3 plus 2x to the fourth in the denominator. And we'll have to multiply by 2 because of chain rule. So the fourth derivative at 0 is negative 96 over 3 to the fourth, which is 81. I think I did that math right. Now that reduces probably, but I'm not going to worry about it. All right, so we're saying ln of 3 plus 2x can be approximated by f of 0 plus f prime of 0 times x plus, but really minus here, f double prime of 0 times x squared over 2 factorial. Again, if you tend to forget things, to write things down, I'm being kind of risky by not writing this down ahead of time. If you think you're going to forget the factorial, then write the step above this, which is f of 0 plus f prime of 0x minus f double prime of 0 x prime, or x squared over 2 factorial, etc., etc. I'm just going to try to be careful here. So plus f triple prime of 0, kind of saying it out loud to myself, times x to the third over 3 factorial minus 96 x to the fourth over 81 4 factorial. Okay, this is my fourth Maclaurin polynomial. That's all we had to do with that. Okay. Find the third Taylor polynomial about x equals 4 for this function. So we need to, this is our c, n is 3, so we have to get out to 3 derivatives. So f of x is radical x. We're going to evaluate f of x at 4, and we get 2. I feel like we just did this one in a previous worksheet. F prime of x, it's good to practice again though. F prime of x is 1/2, x to the negative 1/2. F prime of 4, it's 1 over 2 times 2. F double prime will be 1/2 times negative 1/2. And then x to the 1/2 minus 1 will be x to the 3/2 down in the denominator. F double prime at 4 will be negative 1 over square root of 4 is 2. 2 to the third is 8. 8 times 4 is 32. Right? Oh, wait. What did I screw up here? Oh, no, I'm okay. Sorry. I'm okay. All right. Okay, and then the third derivative, which is our last one, negative 1/4 gets multiplied by negative 3/2. So that's positive 3/8. X to the 3 halves, when you subtract 1 or add 1 in your denominator, you're getting x to the 5 halves in the denominator. And then the third derivative, when you plug in 4, is 3 over 8 times 2 to the 5th. 8 times 30, 32. Wrote that backwards. And what is 8 times 32? Let's see, that's 16,256. Okay, so radical x can be approximated by f of 4 plus f prime of 4 times x minus 4 plus f double prime of 4 times x minus 4 to the second over 2 factorial plus f triple prime of 4 times x minus 4 to the third over 3 factorial. That's our approximation for radical x. Find the third Taylor polynomial about x equals 2 for f of x equals ln x. Right? So f of x equals ln x, and we're evaluating at 2. So the first term is ln 2. F prime of x is 1 over x. F prime at 2 is 1/2. F double prime of x is negative 1 over x squared. F double prime at 2 is negative 1/4. Last one, f triple prime of x is going to be positive 2 over x to the third. I'm only doing this fast because I've done this a lot. Also, this is my third homework assignment in a row today. I've done some of these problems quite a bit, so that's the only reason I'm able to go fast on that. So that's 1/4. Okay, and then we want to build this. So ln x can be approximated by f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared over 2 factorial plus f triple prime of 2 times x minus 2 cubed over 3 factorial. All right. Find Lagrange's form of the remainder for 1 over x plus 1 about x equals 0 for P4. So let's just say we don't have this memorized. We probably don't. This is kind of later in the chapter. We'll memorize that, or maybe chapter 10. I can't remember. But let's just go ahead and build this one. So for P4. All right. So f of x is 1 over x plus 1. Let's get out to 4 derivatives, which is, remember, this is x plus 1 to the negative first. So you're going to be doing it just like these derivatives, but you're going to have an x plus 1 in here. So this one will be negative 1 over x plus 1 squared. And then the second derivative will be 2 over x plus 1 to the third. The third derivative will be negative 6 over x plus 1 to the fourth. The fourth derivative will be 24 over x plus 1 to the fifth. And because I know I'm going to need a formula for the fifth derivative, we might as well take it out that far. Because remember, when we're doing error, we always need like n plus 1. So the fifth derivative at x will be 24 times 5 is 120, negative technically, over x plus 1 to the sixth. All right, so what are they saying? They're saying the difference between, it'll still be in terms of x. Okay, the difference between 1 over x plus 1 and P4 of x will be equal to the remainder at 4 of x. We don't have a number to plug in or anything like that for this one. And that's less than or equal to the fifth derivative max value times x minus 0 to the fifth over 5 factorial. And I just came up with a formula for this. Now remember, we were trying to find a max value. So z sits somewhere between 0 and x. And I don't know if x is positive or negative. So let's just assume it's positive for now. So I could plug in 0, and in absolute value, I could get 120 over 1 to the 6th. Or if I get 120 over 1 point anything to the 6th, that will be smaller. So this is the max. Now, if x can be negative, then I think I'll get a different error for this, which is kind of strange. So I guess I would still have a 120 there. So I don't want to overthink this. I'm going to put a star on this one. I want to let x just be something positive, and then we'll think about that more in class, I think. So, okay, so what is the fifth order derivative here? The max value is 120 times x to the fifth over 5 factorial. Well, 5 factorial is 120. So the maximum here would just be x to the fifth. That doesn't seem right. Times over. Now, maybe I do have to just put in a z plus 1. Maybe I have to leave my z in there. 120 over z plus 1 to the 6th, because we don't know if z is going to be positive in this case or negative in this case. So I think we better leave it here. So Lagrange's remainder would just be the absolute value, or let's just, this would be positive anyway. Let's just write it as 120 x to the fifth. Oh no, the 120 canceled, sorry. The 120 does cancel with the 5 factorial. So all we would have left is x to the fifth over whatever the max value for z plus 1 to the 6th is. So it might just be x to the fifth if x is like say x is 0.1 or something. But depending on, we don't know if the max, like if x is negative, then, yeah, if x is a negative decimal, then that would make 120 divided by 0.5 to the 6th, for example, is bigger than 120 divided by 1 to the 6th. So we have to leave that in place for this one. So this is as far as we can say in absolute value. This is as far as we can say that we can go with that one. That's kind of a weird question. We usually have something else with it. Like what would x be to keep the error less than something, or they tell us x is positive or negative or whatever. All right, for this one, find Lagrange's form of the remainder for sine x about x equals pi over 6 for P4. So, all right, for this one, I don't have to do all the derivatives because remember, if we're just trying to come up with a max, n plus 1 at z, if we have sine or cosine, it's going to equal 1. So I'm going to get right down to setting this up. So this is just saying you can approximate some sort of sine x. Let's see. So some sort of sine x actual value minus our P4 approximation. And that'll give you a remainder of the fourth order at x. That's got to be less than or equal to the absolute value of the fifth derivative evaluated at not x but z. Max value there, times x minus pi over 6 to the fifth over 5 factorial. And all I know about this error bound here, this fifth derivative, is that it's probably going to be 1. So all we can say for this is that it will be whatever x minus pi over 6 to the fifth power is divided by 5 factorial. That will be our max. And it's still an absolute value because to a fifth power could be negative. Approximate e to 4 decimal place accuracy. So this is e to the first, which means they're asking us to approximate f of 1 if f of x is e to the x. And the good thing about that is we have a Maclaurin series for e to the x. So we do know that e to the x is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Okay, so what does that do for me? Let's set up our, we want 4 decimal place accuracy. That means we want 0.00001. All right, now the 1 is kind of questionable, actually. Like, I guess if you're going max error, I would say 9, but they always do 1 in our textbooks, and so I'm just going to go ahead and do that. All right, so this means that we would be saying, what's the difference between E and our, we want 4 decimal place accuracy, so we don't know how many places this is going to be, but we are plugging in 1. It's equal to some sort of remainder if you plug in 1, and that's less than or equal to the n plus 1th derivative at z times 1 minus 0, this is Maclaurin, c is 0, to the n plus 1 over n plus 1 factorial. And we want that to stay less than 0.123400001. All right, so what about this? Every derivative we take, if f of x is e to the x, every derivative, is going to be e to the x. So what's the max value? We're looking between 0 and 1 for z. So that means that we could have e to the 0, or we could have e to the first. E to the first is bigger than e to the 0, right? So now I know that this is e times 1 to the n plus 1, I don't need that, over n plus 1 factorial. That's got to be less than 0.00001. And what is that? 1/10,000th? No, that's 10,000. 1/100,000th, I think. I'm just going to use my calculator for this. Or you can flip this around. What is that? That's 1/100,000th, right? Yeah. Okay. So this is 100,000 is less than n plus 1 factorial over e. So that's what I'm going to pop into my calculator over here. So x plus 1 factorial divided by e. And I'm looking on my table for when does that get me bigger than 1,000? I don't know why this is skipping so much. It looks like when n equals, I'm getting n equals, oh, not 1,000. What did I say? 1,000. Sorry, I'm used to 1,000. 100,000. So let's see, 14,832, 133,000. So n equals 8 is what we need. So this is true for n equals 8. Approximate e to 4 decimal place accuracy. So that means you would need to take this out to 8 places. So e to the first is e to the first is about equal to, we need to go to 8 places. So we're plugging in 1. Wait, is that right? We're plugging in 1, f of 1. Oh, yeah, that's right. Sorry, because e is 2 point something. Okay, so 1 plus 1 plus 1/2 plus 1/6 plus 1 over 4 factorial plus 1 over 5 factorial plus 1 over 6 factorial plus 1 over 7 factorial plus 1 over 8 factorial. I only know 1 through 5 factorial off the top of my head, and I don't want to do math for the other ones. So 2 plus 1/2 plus 1/6 plus 1/24 plus 1 over 120 plus 1 over 6 factorial plus 1 over 7 factorial plus 1 over, I have to go to 8, right? 1 over, 8 factorial. And let's remind ourselves about e. Did we get 4 decimal place accuracy? Yes, 1, 2, 3, 4. We matched for the first 4 decimal places. So that's pretty good. Let me split this and write out what I got there. So E is about 2.71827877. All right. Approximate the sine of 3 degrees to 5 decimal place accuracy. This is a bit obnoxious. Why did I do 3 degrees? I don't know. I'm not the maker of these worksheets. I was just generously given them, so I cannot complain about them, can I? So, okay, so sine of pi over 60. That means that we are trying to 5 decimal place accuracy. We're trying to get 1, 2, 3, 4, 5, 1 here. That'd be 1/1,000,000th, right? I believe so. To get it out to 10, 1, 2, 3, 4, 5, 6. Yeah, 1/1,000,000. I don't know why I'm having such a hard time with decimals today. Yeah, okay. Anyway, approximate sine of pi over 6. Use some sort of Taylor polynomial to approximate pi of 6. That gives us a remainder of some sort when we plug in pi over 6. That's less than or equal to the 7th derivative, max value at z, times pi over 6 minus 0 to the 7th over 7 factorial. We want to keep that under 1/1,000,000. Because we're looking at a sine function, the max value is 1. So that's great. So we really just have pi over 6 to the 7th over 7 factorial is less than this fraction. I'm going to flip it around to make numbers easier to look at. 1,000,000 needs to be less than 7 factorial over pi over 6 to the 7th. So let's, wait, where's an x? Oh, I just went ahead and plugged it right in, didn't I? Oh, wait, I just made up a number. Sorry. We don't have a 6. These aren't 7s, these are n's. Okay, I got ahead of myself there. So this is n. This is n plus 1. This is n plus 1. I've done too much math today. I'm sorry. This is n plus 1 factorial. There we go. We do not know. This is not 6. I was looking at a pi over 6. It's still true that the n plus 1th derivative will be 1. So let's try this again. I noticed I did something wrong when I didn't have any sort of x to plug in. Okay, so let's get that into our y equals. I am plugging in x plus 1 factorial divided by pi over 6 to the x plus 1 power. Go into my table, and I'm looking for a number bigger than 1,000,000. 3,000, 34,000, 467,000, 7 million. So it looks like n equals 7 is what I'm getting. Wait, why am I getting n equals? Oh, gosh, and it's not a 6. It's a 6D. Guys, I'm making all sorts of errors. Let's insert a 0 and see if that fixes things. Well, that's a lot faster. Right there, 3 million. So it only takes 3 because these are 60s, not 6s. Having all kinds of problems today. 60, 60, 60. 3 pi over 180 is pi over 60. I wrote it correctly there. Okay, geesh. Okay, so n equals 3 is what I got for that one. Approximate sine. Okay, fine. So approximate sine, 0.3 to 3 decimal place accuracy. So sine of pi over 60 is about equal to, remember, it's x minus x cubed over 3 factorial. And that's all you have to do when it says n equals 3. That's the order that I have to get it out to. So it should be pi over 60 minus pi over 60 to the 3rd over 3 factorial. Let's try that. Pi over 60 minus pi over 60 to the third divided by 6. And then what is the sine of pi over 60? Pretty good. Do we have 5 decimal place accuracy? 1, 2, 3, 4, 5. Yes, we match. So 0.052335953. These 5 places are correct. Okay, let's take a look at this AP problem. We finally are starting to look at some AP problems. In a couple of days, we're going to have more of these than we care to think about, probably. Okay, f of x is given by this function. P of x is the third degree Taylor polynomial about x equals 0. That's our center. And n is 3. Find P of x. All right, so remember, it's smart to build the thing, but you're going to need to do 3 derivatives, and derivatives have a 5x on them, so they're going to be kind of involved here. So f of x is sine 5x plus pi over 4. F of 0 is the sine of pi over 4, which is radical 2 over 2. F prime of x will be 5 cosine of 5x plus pi over 4. F prime of 0 is 5 times the cosine of pi over 4. So 5 radical 2 over 2. F double prime of x will be negative 25 sine of 5x plus pi over 4. F double prime of 0 will be negative 25 times radical 2 over 2. And our last one, f triple prime of x will be negative 125 cosine of 5x plus pi over 4. And f triple prime of 0 will be negative 125 radical 2 over 2. Now to write the polynomial, P of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x to the third over 3 factorial. So here's P of x. Part B, find the coefficient of x to the 22nd. You are not supposed to take derivatives until you get out to the 22nd. You are supposed to find a pattern here. So what is the pattern? Connected to the derivatives, right? So the third derivative had 5 to the third in it. And the fourth derivative the second derivative had 5 squared. The first derivative had 5 to the first. So I know that the coefficient, not including the x, is going to have 5 to the 22nd. I'm not supposed to find what that is. This would be a non-calculator problem. So I know it's going to have that. It's also going to have a radical 2 over 2, just like everything else does. And then what about, is it going to be positive or negative? So let's look at the pattern here. The 0 derivative and the first derivative are positive. The second and the third are negative. The next two, the fourth and the fifth, are going to be positive. The sixth and the seventh are going to be negative. So I'm trying to figure out, like, well, where does that fall in the pattern? You can either keep it going, or you can do some division, right? Like the fourth derivative is going to be positive. So that means like the 20th derivative would have been positive. The 21st would have been positive. The 22nd would be negative because it falls into that pattern, right? Kind of like we do with i's, like what line do you fall on? So it's going to be negative 5 to the 22nd, radical 2 over 2. And don't forget, there's going to be a factorial in there too. I almost forgot. Right? What about part C? Use the Lagrange error bound to show that the actual difference is less than 1 over 100. So again, here's a non-calculator example. So, all right, so we're looking for that actual difference here. And this is a P3, right? So that's going to come out to the remainder 3 evaluated at 1/10. That's less than or equal to the fourth derivative at a max value z times 1/10 minus 0 to the fourth over 4 factorial. And we're supposed to show this is less than 1 over 100. Okay, now be careful. We have a sine and cosine function, but we have numbers out in front of them. So we found the third derivative. The fourth derivative, what's 125 times 5 in absolute value? It's going to be 625, right? 5 times 125, yeah, 625 sine of 5x plus pi over 4. So yes, this max value is 1, but it's 1 times 625. So that max value is 625 over 10 to the fourth times 24. We need to show that that's less than 1 over 100. Or we can flip it around. 100 is less than 10 to the fourth times 24. Let's go ahead and do some math on that. That's 24 with 4 zeros over 625. And I can just kind of multiply this over, right? 625 with 2 zeros is less than 240,000. So I think that's enough to show, like, yep, this is a true statement. Or you could do the math on this and reduce and show that it's 1 over something more than 100. But I think that's enough for me to show that this math is valid. All right. What else? There's a part D. Let G be the function given by, it's been a little while since we saw this. Let G be the function given by G is the integral from 0 to x of f of t dt. Write the third degree Taylor polynomial for G about 0. So do we have room for this? Not really. You might need some extra paper. Let me try to squeeze it in down here. Let's build this one first. So G of x is approximately equal to, we're going about 0, G of 0 plus G prime of 0 times x plus, what are we trying to do? Third degree. G double prime of 0 times x squared over 2 factorial plus G triple prime at 0, x cubed, 3 factorial. G of 0 is the integral from 0 to 0 of whatever, so that's 0. G prime is actually equal to f of 0 times x. G double prime is actually f prime of 0, x squared over 2 factorial. G triple prime is actually f double prime at 0, x cubed over 3 factorial. Okay, do we have that information? Well, remember, we do have an f of x, and so we do have those values. We have f prime of 0 and all that, so we already did the math on that. So I'm going to put that over here. So we have 0 plus f of 0 was radical 2 over 2 times x plus f prime of 0 was 5 radical 2 over 2 times x squared over 2 factorial. F triple prime was, wait, did I skip double prime? Oh, yeah. Not triple. Double prime was minus 25 radical 2 over 2 times x cubed over 3 factorial. That is our G. Okay, let's take a look at this AP problem. Is this our last one? Yes. Okay. This one we have a table. We're kind of going to do something similar to what we just did. So h is a function having derivatives of all orders for x greater than 0. Selected values of h and its first 4 derivatives are indicated in the table above. The function h has these 4 derivatives, and these 4 derivatives are increasing on the interval from 1 to 3. So strictly increasing. Write the first degree Taylor polynomial for h about 2, and then approximate h of 1.9. And is this approximation greater than or less than actual value? So there's a lot to do in part A. First, let's build this thing. We're supposed to say h of x is approximately equal to just a first degree, nothing crazy, first degree Taylor polynomial. That's h of 2 plus h prime of 2 times x minus 2, and that's it. Okay, so h of x is about equal to h of 2 is 80 plus h prime of 2 is 128 times x minus 2. So there's the first part. Use this to approximate, I think I'm allowed to use a calculator, by the way, but use this to approximate h of 1.9. So that would be 80 plus 128 times 1.9 minus 2. 80 plus 128 times negative 0.1. 67.2. Oops, 1.9 is about equal to 67.2. The overestimate, underestimate thing is about concavity, right? Because remember, if you are concave up on a section, even though, now we did use a linear approximation, so this applies, your approximation is lower, less than. If it's concave down, your tangent approximation is greater than. So what do we know about the second derivative? H double prime of 2 is greater than 0. It's 488 over 3. So we know that h of x is concave up at x equals 2. So that's the first scenario that I drew out, which I always have to draw out for myself. You don't have to over-explain this. This is all you have to say. So that means that h of 1.9 equaling 67.2 is less than h of 1.9. Or, you know what? Let me say that a better way. P1 of 1.9, my approximation, is less than actual h of 1.9. Okay. I think I did everything in that part. Part B. Write the third degree Taylor polynomial for h about x equals 2 and use it to approximate 1.9. So h of x is about equal to, I'm not going to write it all out this time. Let's see if I can keep track of it. So it's h of 2 plus h prime of 2 times x minus 2 plus h double prime of 2 times x minus 2 squared over 2 factorial. How far? Third degree. Plus h triple prime, same number, times x minus 2 to the third over 3 factorial. And then use that. We're definitely allowed to use a calculator. Use that to approximate h of 1.9. So 80 plus 128 times negative 0.1 plus 488 times, my pen stopped working. Hold on. Times negative 0.1 squared divided by 3 times 2 is 6 plus 488 times negative 0.1 to the third divided by 3 times 6. So I'm getting 67.986 repeating. Okay. And, I might have had a typo in there somewhere. I'm not quite sure. I have a slightly different thing on my key, but anyway, close enough. Okay, use Lagrange error bound to show that the third degree Taylor polynomial has an error less than that. So Part C is saying we used a third degree Taylor polynomial to evaluate 1.9. That's got to be less than or equal to the max h fourth derivative of h at z times 1.9 minus 2 to the fourth over 4 factorial. And we're trying to show that that's less than 3 times 10 to the negative fourth. So 1, 2, 3, 3. We get this value from the table. The fourth derivative at the max value for the fourth derivative that we're supposed to use is, let's see, we're still centered at 2. We don't want to use the one for 18 or 3 because we're only going between 1.9 and 2, right? So it's got to be 584 over 9. We can't plug stuff in and say, well, it could be this or this. We have to use the table. All right, so 584 over 9 times negative 0.1, but it's to the fourth. Should be positive anyway. We're in absolute value over 4 factorial. And let's just cross our fingers and hope that works. 584 times 0.1 to the fourth divided by 9 times 24. Yeah, that's 0.1232703, etc., which is less than 0.0003. All right, this was a challenging practice worksheet. Please come into office hours if you need help with any of this. And I think that finishes today.